Hello, students. So in the previous class, we left with the modern periodic, Mendeleev periodic table. Now, okay, I said that we are in a very good position now. We have moved up to Mendeleev periodic table. Now, before moving further, let us just try to analyze this periodic table. So he decided to put groups here. Okay, so these are the groups 0, 1, 2, 3, 4, 5, 6, 7, 8. So these groups of elements will have the same properties. This is the thing, or this is the motive behind the Mendeleev periodic table. So it is written here also. So there are 8 vertical groups, which is named that are 4, 3, 1, 1 to 8. And except for group 8, each atom is further divided into 2 subgroups designated as AB. Okay. So here you can see that in each group we have 2 elements. Okay. Okay. This see here, beryllium, magnesium, boron, aluminium. Right. Now here he left it. Okay. These are the vacancies that he left. Okay. So we have here boron, aluminium, carbon, silicon, nitrogen, phosphorus. So in each group we have two further subgroups which are A and B. Except in group 8 where we have more than 2 elements. Here we have 4 elements. Here again we have 3 elements. Here we have 3 elements, 4 elements again. Now the elements which lie on the left hand of each group constituted of group A, while those on the right hand side of constituted of group B. So this is this lithium, potassium, rubidium, cesium. So they all are of group A, whereas on the right hand side, sodium, copper, silver, gold, they are all are where? They all are of the group B. Now this subdivision is made on the basis of difference in the properties. So again their classification as A and B is based upon the properties that we have. The group 8 contains ninth element in 3 states. Okay, each containing 3 elements. Group 0 consists of inert gases. So there are 3 elements you can see here. 1, 2, 3, 1, 2, 3, 1, 2, 3. So 3 elements are present in the group 8. And group 0 consists of inert gases. So these are all the inert gases that we have. Okay, these are all the inert gases that we have. Now, this gallium and germanium were left vacant. So this is called as eka aluminum. This is called as eka silicon. So although it is mentioned here, but at that time it was not discovered. Now, apart from groups, we have horizontal rows. So we have vertical rows, we have horizontal rows also, which are numbered from 1 to 6. So see here, 1, 2, 3, 4, 5, 6. Okay, so they are numbered from 1 to 6. 1, 2, 3, 4, 5, and 6. So these are series. 1, 2, 3, 4. These are series, and where this one block is called as one period. So 1 block, 2 block, 3 block, 4 block, 5 block, and 6 blocks are there. Again, you can see that the compounds that can be formed are also mentioned. So that R, so since it is a inert gas, it will not form any oxide. So later on, oxides were discovered. That is a different thing. But at that time, it was considered that noble gas don't form any compound. So it is written as R. Then this is R2O. This forms RO. This forms R2O3. This forms RO2. Then again with hydrogen also it is given RH4, R2O5. Okay. Now, with the help of this, what was the significance of magnetic table? So with the help of this table, we can do a systematic study of the element. So if you know the properties of one of the elements in the groups, you can predict the properties of the other elements. And this was our main motive. And the second thing that we have focused upon was the prediction of new elements. And in addition to that, the properties of those new elements also. So therefore, while rearranging the elements according to properties, Mendeleev left some blank spaces, and these blank spaces, these gaps represented the unknown elements. Now, with the help of this, he also corrected some of the doubtful atomic weight. Okay, it has helped in correcting the doubtful atomic weights of sub-elements. For example, beryllium was assigned as the atomic weight of 13.5 on the basis of its equivalent 4.5 and valency as 3. But if beryllium has a atomic weight of 13.5, then it would have placed between carbon and nitrogen. But no vacant space were available between carbon and nitrogen. So beryllium could not justify its position. So later on, its atomic weight came out to be different. Okay, it was between lithium and boron, and it was 9. Okay, it was not 13.5. It is 9. So in this way, since the Mendeleev placed it there, placed the boron there. So if you see at the periodic table here, so if you just find boron, so here is boron. Okay, so it is placed between beryllium and carbon. So since it is placed between beryllium and carbon, it should have an atomic midweight that should be intermediate between these two. But since uh, it was written as 13.5, so it was wrong. So when they predicted it as wrong or it was doubtful. So later on, with the advanced spectroscopic method, it was found to be 11. Clear? Now, what were the defects in Mendeleev table? So let us now talk about the defects. First of all, the anomalous position of hydrogen. So if you look at the table back again here, then you will find that all the groups have two elements except these group. Okay, if I talk about these group, so hydrogen, lithium, and sodium. So there are total of 3 elements that are present. So that is the difficulty. Okay, so we cannot define where the hydrogen will lie. And let me give you a very interesting fact that till date, the position of hydrogen is not accurate. Okay. Why? Why is it so? Why he was not able to classify it? So although he was going through the way of properties, the difficulty came. The difficulty was that it resembles the element both of the alkali and halogen metal in terms of properties. Okay, so some properties were resembled were in resemblance with the alkali metal, where other properties were in resemblance with the halogens. Therefore, the position of uh, hydrogen in the modern periodic table is still controversial and anomalous. Second thing, anomalous pairs of elements. So some elements have higher atomic weight which precede the element with the lower atomic weight. Okay, he said that the atomic weight are the kind of the deciding factor or the periodic function of the for properties of that element. But some of those, like if you talk, we have seen it that he placed iodine here. Okay, so if you go back here, so iodine is placed here, right? Okay, so where is the one? Yeah, iodine is placed here, 126.9. So although it has a greater atomic weight than tellurium, it is not placed between antimony and tellurium. It is placed after tellurium. So this was kind of not justified, but still he did it with the help of physical and chemical properties. But the law he predicted was wrong. Okay, so no justification was provided for this ambiguity. Ambiguity means exception, I would say, or you would say that for this misbehavior. Next thing, what about isotopes? So if you are saying that okay, atomic weight are the periodic function, atomic weight are the periodic function. So means the physical properties are the periodic function of atomic weights. Then the isotopes would show different properties because their atomic weights are different. So if you to consider the case of chlorine, which has 35 and 37 as the possible atomic weight, then these both elements which have different physical properties and those both have should both have the different position in the periodic table, but it is not so. Okay, because they both have the same properties. There's no change in the properties in case of isotopes. Similarly, for the isotope of hydrogen, which are protium, deuterium, and tritium, so it has the atomic weight of 1, 2, 3, and so they should be placed at different places because they have a different atomic number. And since the properties are dependent upon the atomic weight, so it should be placed differently. However, isotopes and element have not been given different places in a periodic table. So this was a question to Mendeleev periodic table. Next, some dissimilar elements are grouped together while some similar elements are placed in different groups. For example, lithium, sodium, and potassium are grouped together with coinage elements such as copper, silver, and Au. Okay, although their properties are quite different. So if you just look here, then we have gold, okay, gold, silver, and copper. So along with it, we have sodium also. So this is the difficulty. We can't place sodium in this group. Okay, so this are again some of the anomalous properties that cannot be explained. Next, position of element in group 8. So no proper place has been allotted to the ninth group of the ninth element of the group 8, so which have been arranged in three triads without any justification. This is the thing. See here. So they are just placed in one row without any justification. So why are they placed here? What is the reason behind it? What is the motive behind it? It was not explained. So according to modern periodic table, now we'll move to the atomic periodic table. Okay, now we'll move to the atomic periodic table and see uh, what was the magic of periodic table. This periodic table, the properties of elements are repeated after certain interval when these elements are arranged in order of their atomic number. So rather than arranging them in their atomic weight, modern periodic table uh, deals with the atomic number. Further, critical examination of the electronic configuration of various elements clearly indicate that with the gradual increase in atomic number, there occur a repetition of similar outer electronic configuration. So this you can see that if you just refer to a group, you will see that in a group, the electronic configuration, the valence configuration is same. Okay, so I'm not talking about some anomalies that we have, but still it is same. By correcting these two observations, we can say that the cause of periodicity is not your atomic weight, but it is the outer configuration. So if outer electronic configuration, so if there is a similar outer electronic configuration, there is a repetition of the properties. Okay, so this is the periodic table of the so this is the Mendeleev periodic table again in a different form. So here we have hydrogen, lithium. So we have group 1, 2, 3, 4, 5, 6, 7, 8, and here we have also 1, 2, 3, 4, 5, 6, 7, 8. So these are the I have just put this table here because this also include the Daubernier traits that we have. See, these are the Daubernier traits. So this is the Daubernier trait. This one is the Daubernier trait. This is the Daubernier trait. Okay. Now you can just look at it. Okay. Now next. So we have seen it already. So we must bear that Mendeleev developed periodic table in the time where nothing was known about this structure of atom. Means there is no insight in the structure of atom, right? But however, in the beginning of 20th century, it witnessed the profound development of theories about subatomic particles. So in 1913, Henry Moseley observed regularity in characteristic X-ray spectra of the elements. Okay, a plot of under root nu against atomic weight gives a straight line, and not the plot of under root nu and atomic weight mass. Okay, so this is the point where we turn our faces away from the Mendeleev periodic table. Okay, so what did Moseley did? He just plotted a graph between the characteristic frequency of that element against the atomic number and not the atomic weight, and then he found a similarity in properties. He thereby showed that atomic number is more fundamental of an element rather than atomic mass. And then the periodic table was accordingly modified, which is known as modern periodic law. Okay, so this law stated that, so as I have already discussed, the physical and chemical properties of the elements are the periodic function of the atomic numbers rather than the atomic weights. The periodic law revealed the important analogy among the 94 naturally occurring elements. Neptunium and plutonium like actinium and proactinium are also found in the pitch blende and ore of uranium. So this kind of stimulated and renewed interest in inorganic chemistry and has carried into the present criteria of artificially produced short-lived elements. Clear? Okay. Now we know that the atomic number is equal to the nuclear charge or the number of electrons in the neutral atom. Now it is easy to visualize the significance of quantum number, electronic configuration, and periodicity of elements. So with this new modification, everything started to make sense. Okay, so why is this electronic configuration is in this way? What is the significance of the number of electrons and protons, and each of these things started to make sense. It is now recognized that the periodic law is essentially the consequence of periodic variation in the electronic configuration, which indeed determine the physical and chemical properties of elements and their compound. So we are now good to go with the electronic configuration rather than the atomic weight. So I would not say atomic number, I would say more specifically and more loudly that it is the electronic configuration that is the deciding factor. Now, from that time, numerous forms of periodic table were devised from time to time. Some forms emphasis on the chemical reaction and balance, while other on the electronic configuration of elements. Now, the current form is known as the long form of the periodic table of the element and is the more convenient and widely used form. The horizontal rows, which Mendeleev called series and are called periods now, and the vertical columns are still called groups. Okay, so in place of series, they are called now as periods. Okay, so this is the modern periodic table that we have. So if you see here, then these are the groups 1A, 2A, 3A. Now in nowadays they are not called as 1A, 2A. They are now called as 1, 2, 3, 4, 5, 6. Simply it is this will be 13, 14, 15. So this is the old way of representing the periodic table that includes A along with the Roman numerals. We have the alphabets also, but it is not the new form. On the left hand side, okay, we have the periods which are 1, 2, 3, 4, 5, and it goes up to 7. In addition to that, we have two rows that are placed in the bottom, which are called as lanthanide and actinide. So when we will move forward, we will study about this in the class 12th also, about this lanthanide and actinide in a different chapter. These are the, now if I just try to classify it quickly, then these are called the S block elements, these are called the P block elements, this is called D block elements, and these are the F block elements or the inner transition elements. Clear? Now the noble gas is also placed in a very appropriate position, that is here. Now still we are writing hydrogen on top of this, so we are not placing it anywhere because it has a resemblance of lithium of this alkali metal also, plus it has resemblance of this chlorine, bromine and iodine also. Means either it can be placed in group 1 or it can be placed in group 17. So both are good to go, right? Both are good to go. Now elements having similar electronic configuration in their atoms are arranged in vertical columns. So if you talk about the groups, so this will have the same electronic configuration. There will be some disparity, but apart from the disparity, we will see that they have the same electronic configuration. The 7th period is incomplete, like the 6th period would have theoretical maximum of 32 elements. If you look here, this is the 7th period. Okay, this is incomplete, right? Now there are altogether 7 periods, we know that, and they are 1, 2, 3. So we have seen this. Okay. Now in this form of periodic table, 14 elements of both 16 of 6th and 7th period are placed in a separate panel at the bottom. So we have talked about it. They are lanthanoids and actinoids which are placed on the bottom. Now the naming of the new element have been traditionally the privilege of the discoverer, and the suggested name was ratified by the IUPAC. In recent years, this led to some controversy. The new element with very high atomic number are also unstable, that only minute quantities, sometimes only a few atoms of them are obtained. Their synthesis and characterization therefore require highly sophisticated, costly equipment and laboratory. So, although the old elements have the liberty of naming that elements in the against the name of the discoverer, but nowadays IUPAC has you can say they have regulated some norms, and now according to the norms they are named. Okay, so we will see that IUPAC nomenclature also. So such work is carried out with the help of competitive spirit only in some laboratories. So here we are talking about the rare elements, the rarest of rare, whose only some atoms could be obtained. Okay, so they are rarest of rarest, and there is a very high competitive spirit or the one with only the high competitive spirit, can be indulged in such a fascinating work of finding this new elements, and they are done in some laboratories across the world. Okay, only in some laboratories. Scientists, before collecting the reliable data on the new element, at times get tempted to claim your discovery. For example, both American and Soviet Union scientists claimed credit for discovering element 104. The Americans named it Rutherfordium, where the Soviets named it Kirkwoodium. Okay, so they both gave different names. So this kind of created controversy that how should we name it? Okay, who should get the credit of the naming of the compound? Now, to avoid such controversy, IUPAC had made some guidelines that any new element that will be discovered will be named according to that guideline. Right? So here we have the guideline. So we have digits from 0, 1 to 2. So for each digit, we have a root name. Like for 0, we have nil, 1, we have un, 2, we have bi, 3, we have tri, 4, quad, 5, pent, 6, hex, 7, sept, 8, oct, and 9, n. Now they can be again abbreviated with a single word. Nil has n, un has u, bi has b, tri has t, quad has q, pent has p, hex has h, sept as s, oct as o, and n as 9. So this is the thing. Now, uh, but how do we name it? Suppose we have an element whose atomic number is 102. So we'll take the roots. So for 1, we have root as un, so we'll write un first. Then we have 0. 0 has a root name of nil, so unnil. Then we have 2. So 2 has a root name of bi, so unnil bi. So once we have written all the roots according to the numbers that we have written, we have arranged it. Now we will just write um against the name. So that will give us the name of unnil by m. So this nomenclature is for the elements which are having a atomic number greater than 100. So here are some names of it. So first of all, if I talk about the trivial name of 101 element atomic number, it is Mendeleevium, right? Now 101 means 1 will have un as the root, 0 will have nil as the root, and 1 again will have un as the root. So unnil unnium against IUM at the last. So IUM is the last 3 term that should be placed. We have seen this one, unnil bium. What about this? So again un for 1, nil for 0, and tri for 3. So unnil trium. What about 104? So 1 stands for again un, 0 for nil, 4 has quad. So unnil quadium. So IUM should be placed every last of it. Then we have unnil pentium, right? For 106, we have unnil hexium. 107, 7 has septium, so unnil septium. Okay, 8 has oct, so unnil octium, and has 9 has n, so unnil ennium. So this is the name. Okay, now if I talk about the triple name, then 101 is named after Mendeleev, which is Mendeleevium. 102 is Nobelium. 103 is Lawrencium. 104 is Rutherfordium. 105 is Dubinium. 106 is Seaborgium. 107 is Borium. 108 is Hasmium. And 109 is Mithrium. Okay, clear? Now moving to other elements. So suppose we have atomic number of 110. So you can just try this out. It will be a fun activity. Suppose I'm trying it for 110 again. So 2, 1 are there. So un, then 0 we have nil and ium at the last. So nilium. What about this? Triple 1. So 3 un will be written unnium. Okay, nium. What about 112? So un for 2, 1 and then bium. Then this one un trium. This will have un quadium. This will have un pentium. This will have un hexium, un septium, and un octium. What about the IUPAC name? So 110 is Dam Stadium. Okay, 111 is Rongatium. 112 is Coppercinium. 113 is Nionium. 114 is Flerovium. 115 is Moscovium. 116 is Livermorium. 117 is Tennyson, 118 is Ogansen. Okay, so these are the trivial name you don't need to remember, but you should know how to name the compound that have an atomic number greater than 10 when according to the current IUPAC guidelines. Thus, the new element first gets a temporary name, which is against the discoverer, with symbol consists. So the temporary name, sorry, not the discoverer, but the IUPAC guideline. Later, permanent and symbol are given for a vote of IUPAC representative from each country. So the a voting is being done, and then according to the voting, the scientist or the one which is more deserving for discovering that element gets to name the compound against the discoverer. The permanent name might reflect the country, or it may be country in which the element was discovered, or it may be a tribute to a notable scientist. So see, it is very obvious. So suppose for example, this Rutherfordium is against the great scientist Rutherford. Okay, what about this? Bohrium is against Bohr, Niels Bohr. Okay, Lawrencium is against the name of a place, right? Here also Damston is against Damstadium is against Damston. Okay, so official names of all elements have been announced by the IUPAC. So IUPAC at last decides that which will get which name. Now, what would be the IUPAC name and symbol for the element with the atomic number 120? So how will write the symbol? By using the one letter code that we have. Okay. So for 120, the name would be un by nelium. So 1 stands for un, by stands for 2, and nil stands for 0. So un by nelium. What will be the symbol? So un has a one letter code of U, by has a one letter code of B, and nil has a one letter code of N. So UBN. UBN will be the symbol. Okay. So this is the thing that is written un by nelium. Okay, and the symbol is UBN. Clear? Okay. So with this, we have completed this classification of elements. Means not the class. Yes, I would say that we have completed the classification of element. But now we will move to the periodicity properties. That how was the periodicity dealt? Okay. This was for today's lecture. Thank you.